Next, I'm going to explain how to find the derivatives of inverse trig functions. And having a basic understanding of inverse trig functions is very important. Remember how trig functions normally work. Your input is an angle measure. Your output is this ratio of sides, some decimal value. So first of all, you've got to be able to think about what you're really doing here when you work with an inverse trig function. Really what you're trying to do is you're trying to find an angle measure. So what you're really trying to do here when you talk about finding the inverse sine of something, you're actually trying to find, if you want to think about it this way, the angle. In other words, the input's going to be a decimal or fraction, the output's going to be an angle. The angle whose sine is x. That's really what you're trying to do there. So we don't really know how to find derivatives of inverse sine functions. We need to turn this into something that we do know how to find the derivative of, which of course would just be the regular sine function. So it's an inverse function. Inverse functions switch the input and the output. I'm going to rewrite this as x equals the sine of y. That would be the inverse function, and that would be another way of writing that function. Well, guess what? We do know how to work with the sine function. So if I wanted to find the derivative of this, it's actually very simple. Before I do that, though, I need to make the link to triangle trig. And of course, I saw that in the last video. If you haven't seen that last video, you might want to go back and take a look at that. So I'm going to draw a right triangle here. And remember what this is saying. This is the angle whose sine is x. That's saying that y is the angle. And we need to figure out what x means in this problem. Well, based off the sine definition, if you remember your SOHCAHTOA rules, sine is equal to the opposite side over the hypotenuse. So we're saying that the sine of y is equal to, it really should be a fraction. X as a fraction is x over 1. And that's the opposite side over the hypotenuse. I can actually go backwards and I can put those values on my triangle. So here, the opposite side is going to be x based off this statement, and the hypotenuse is going to be 1. Now, the Pythagorean theorem relates sides of right triangles. I know that this side squared plus this side squared is equal to that side squared, which means I can work backwards here. I know that this side squared minus this side squared is going to be the square of this side, okay? So I know that 1 squared minus x squared will be the square of that third side. So I can take the square root, and that tells me that that side is going to be 1 minus x squared, the radical of that entire value. So you can actually go in and algebraically label the sides of your triangle based on the original statement. Now, at the moment, that doesn't seem useful, but it will be, trust me. So I come back, and I want to take the derivative here. The derivative, of course, is going to be, well, derivative of x, of course, is just 1. Derivative of sine is cosine, so it'll be cosine y. Now, this is something we haven't really talked about yet, but the chain rule says I have to multiply by the derivative of the inside function. Normally, if it was an x, the derivative of x is just 1, and that's insignificant, so we don't normally write that, and honestly, we don't normally think about that if it's just an x. But if it's a y, we don't know how to handle that other than that's an inside function. So I do need to multiply by the derivative of the inside function. That's what that value is right there. Again, it seems a little strange, but you know, it does follow the chain rule and it follows the things that we've learned up to this point. So what do I have here? Well, I have this statement that says that 1 is equal to the cosine of y times y prime. I want to solve for y prime. Okay, that was the whole idea here. I'm finding the derivative of the inverse sine function. And this is just the same function written in a different form, but the derivative should still work out to be the derivative of this thing up here. So what I really want is y prime. Well, I can divide both sides by cosine of y, and that's going to give me y prime. So I know that y prime is going to be equal to 1 over the cosine of y when I divide both sides here. And so you look at that and you think, well, great. So the derivative of the inverse sine function is just 1 over the cosine of y. And then you remember, this function here was written in terms of x. This is written in terms of y. I don't want that function written in terms of y. So I'm going to need to go back over here and try to figure out what's going on. Now, if you remember, y is an angle, okay? I have a diagram over here relating all of these values. If I want to find and replace the value of cosine of y, I can go to my diagram that has a triangle, right triangle, with an angle measuring y, and I can figure out what that is. So cosine, if I want to find the value of cosine of y in terms of x, cosine is just the adjacent side over the hypotenuse. So a over h. Well, the adjacent side is 1 minus x squared, radical. The hypotenuse is 1, and so that's just going to be 1 minus x squared, all under a radical. I can replace that. That's the value of cosine y. I can replace that in my statement. And so my final derivative here, y prime, is going to be equal to 1 over, replace the cosine of y with that 1 minus x squared, and that is the derivative of inverse sine. Not quite as catchy as some of the other derivatives, but definitely something that links to things that we've learned in the past. If I want to find the derivative of the cosine function, the inverse cosine function, it's very much the same thing as finding the derivative of the inverse sine function. You can see here I have y equals inverse cosine of x. In other words, it is the angle whose cosine is x. And once again, I can write that using the cosine function instead, writing this in inverse. That would be x equals cosine of y. Remember that y is the angle measure. Once again, I can make my own right triangle here. The angle measure is y. Cosine, in the SOHCAHTOA rules, cosine, of course, is equal to the adjacent side over the hypotenuse. So it's saying that the adjacent side over the hypotenuse is x over 1. Adjacent side, hypotenuse. So there's my angle. Adjacent side is x. Hypotenuse is 1. And if I wanted to find the third side, it's going to be the hypotenuse squared minus this side squared is equal to the third side squared. So that would be 1 squared minus x squared is equal to the third side squared. I can take the square root there, and of course that's just going to be radical 1 minus x squared. Hopefully not too bad. Now, if I want to take the derivative here, I have x equals cosine of y. The derivative of x is 1. Derivative of cosine is negative sine of the same thing times the derivative of the inside function. Again, we don't really know a lot about this, but we're going to call that y prime. Just like before, I want to solve for y prime. So what am I going to do here? I'm going to divide both sides by the negative sine of y. And when I do that, I end up finding out that y prime is equal to 1 over the negative sine of y. I'm going to move that negative sign out in front here. Again, do I want a function written in terms of y? No, I want a function written in terms of x. So I need to replace sine of y over here. I know that sine is equal to the opposite side over the hypotenuse. And so I have my triangle drawn here for angle y. The opposite side is radical 1 minus x squared. The hypotenuse is 1, and so the sine is just going to be radical 1 minus x squared. And if you think that looks a little familiar, that's because that's the same thing we had back before with the inverse sine derivative. So I'm going to replace the sine of y with this value right here, and that means that the derivative is going to be negative 1 over radical 1 minus x squared, and that is the derivative of the inverse cosine function. Notice, very important, the only thing that changes from the inverse sine derivative is the sign. It's negative instead of positive. For my final example, I want to show the derivation of the inverse tangent derivative. So of course, if y equals inverse tangent of x, y is the angle whose tangent is x. So once again, I can draw a picture of what's happening here. Y would be my angle. Tangent is the opposite side over the adjacent side. So if I rewrite this using inverse notation, that would be x equals tangent of y. Okay, if x is my tangent value, that's my opposite over my adjacent side. So it's telling me that my opposite side is x, telling me this time that my adjacent side is 1, which means the hypotenuse is going to be this squared plus this squared, basically the radical of that. So it's going to be radical 1 plus x squared. It's 1 squared plus x squared, Pythagorean theorem. Okay, same thing as before. I can take the derivative of this. The derivative, of course, is just going to be 1 equals, remember the derivative of tangent is secant squared of the same thing, times the derivative of the inside function, okay? I can divide both sides by secant squared here, same thing that I did before. And I know that secant is the reciprocal of cosine, so I'm going to write this as y equals, y prime equals cosine squared of y instead. That'll simplify things down a little bit easier, make it easier for me to work with my different rules. So anyway, if I come over here to my triangle, again, I want to write an expression for the cosine of y. Well, cosine is equal to the adjacent side over the hypotenuse. Here, the adjacent side is 1. The hypotenuse is radical 1 plus x squared. And so that is going to be my value of cosine of y. Notice, however, that cosine of y is being squared. So I'm going to substitute in for cosine. It'll be radical 1 plus x squared squared equals y prime. And of course, when I square that, it's 1 over 1 plus radical 1 plus x squared. And when I square that, 1 squared is 1. The radical will disappear here, and I'm going to have that the derivative, actually the easiest one to remember, the derivative of the inverse tangent function is equal to 1 over 1 plus x squared. I'm going to show one derivative of a reciprocal inverse function. I'm going to do inverse secant. Inverse secant's a little bit different than the others as far as what the final equation ends up looking like. There's just a little bit of a tweak I'm going to have to make here. So if you look at this, of course I can rewrite this as inverse. That's going to be x equals the secant of y. Okay, we know that secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is going to be hypotenuse over adjacent. Okay, just like before, I can make my right triangle. My angle is y here, and it says that the secant is x. Okay, so x over 1 is the secant. That's my hypotenuse over my adjacent side. So my hypotenuse is x, my adjacent side is 1. The other side over here then is going to be the hypotenuse squared minus 1 squared, basically the radical of all of that. So that's radical x squared minus 1. So we get our triangle labeled here. Okay? Now to finish this thing out, I'm going to take the derivative. Derivative of x is 1. Derivative of secant y is secant of y, tangent of y, times the derivative of the inside function, which is y prime. Okay? Like before, I'm going to divide by everything here. And I'm going to end up with 1 over secant y, tangent y, equals y prime. Again, I've got to make a substitution. This time I have two values I need to replace. So I need to figure out what the secant of y is, and I need to figure out what the tangent of y is. Well, secant is the hypotenuse over the adjacent side. Okay, so the hypotenuse over the adjacent side is going to be x over 1, which of course is just equal to x. Interesting. The tangent, of course, is the opposite side over the adjacent side. The opposite side here is radical x squared minus 1 over the adjacent side, which is 1. And so we get something that looks like that, and I can put that in. Now there's one little thing here. It's not going to seem very important, but in all these other answers we had radicals that were positive values, and we usually had squaring involved, which is going to force negative values to become positive. Technically, when I do my substitution here, it's going to be 1 over x times radical x squared minus 1 equals y prime. We have a very slight problem here because x is the side of a triangle. If I just toss some random x into my function, it's possible that, not realizing that it was supposed to be the side of a triangle, I could put a negative value in. So I have to force that value to be positive, otherwise I can't create a triangle. So here, with the squaring, I don't have to worry about that. Here, I do have to have an absolute value. So when you look at your equations in the book, you're going to see that this has an absolute value around the x. Makes it look a little bit uglier, but you should be able to see that over here it doesn't make any sense to have a negative side length. And so we have to account for that with that radical, with that absolute value.
Here's the chart of the derivatives of the 6 inverse trig functions. And you can see in each case that the function and cofunction derivatives are opposite signs of each other. So from the inverse sine to the inverse cosine, you get a negative. Same thing happening with the tangent and inverse cotangent, and the inverse secant and inverse cosecant. So you really only need to learn the sine, tangent, and secant inverse derivatives, and the rest will be just the opposite signs.
Okay, so here's a quick example of how to find derivatives of inverse trig functions. Basically, if you remember, the inverse sine derivative of inverse sine of x is 1 over radical 1 minus x squared. Okay, you're going to use that same pattern, but this time the inside function is 5x, so it's going to be 1 over radical 1 minus 5x squared. Make sure that whole 5x is being squared. Then I have to multiply by the derivative of the inside function, which of course is 5. So it's going to end up being 5 over radical 1 minus 25x squared. And that is my derivative there. Okay, in part 2, the inverse tangent derivative. Remember that the derivative of inverse tangent of x is 1 over x squared plus 1. 1 plus x squared, I guess really doesn't matter which you do. So in this case it's going to be 1 over e to the 3x squared plus 1 times the derivative of the inside function, which is going to be e to the 3x times 3, since that's the derivative of the inside function of e. And so that's going to be 3e to the 3x all over e to the 6x. Maybe you multiply the exponents here, so it's 3x times 2, power to a power, 6x plus 1, and that's your final derivative.